Welcome back to Arts Learning. In this video, we'll be going over force versus time graphs, as well as how momentum relates to these kind of graphs. Okay, so stay tuned for what's about to come up. So first, let's look at the area under the curve of impulse. Okay, so for example, force versus time graphs. Okay, that's what the name is, right? So we can assume there's time here and force here. So let me actually pick a different color. Yeah, but there's time here, okay, and there's force here. So we figured out in the previous video that the area of this graph, which is force times time, we know the units of that are impulse, right? So the area under a force time graph should give us R, impulse, or J. Now for a triangle, the area is 1/2 times B times H, but it's the same thing, right? This is a spike in impulse or a spike in force and time, because in real scenarios, impulse doesn't always stay stationary like this, okay? Or force doesn't always stay stationary like this. During the course of the collision, the force changes. It either decreases or increases, okay? Because it doesn't stay constant. That's just how the force works. It just moves around. This continues what it's doing, okay? The triangle here is an example of that. Now for a trapezoid, same thing, right? But here, how would we find it? We look at 1/2 A plus B, right? So that's these two lengths, and then times H, which you don't really need to worry about, right? You can just find the areas of these. I'm just showing you how force can be different as time goes on, okay? It doesn't need to be a flat graph like this. And force needs to be on Y, and time needs to be on X, because those units are what give you impulse, right? Force times time. Kilogram meter per second. Okay, so let's find the area and get the impulse here. We have force of constant 5 newtons over 7 seconds. The impulse is just going to be the area of this graph, so 5 newtons times delta t, which is 7 seconds, or 35 joules. Whoops, not joules. Stuck on the last unit. Newton seconds, yeah. Joules was for energy, okay? Newton seconds is for impulse. So that's what the area of this graph would be. Here, similar idea. We split this, right? 1/2 times base, which is 0.4, times height, which is 20. Or you could just, this is 0.2. You can flip this to make it a rectangle. 0.2 times 20. Which either way, anything gives you 4 Newton seconds. So it's not that hard as conceptual, but not that hard to compute, but it's hard conceptually. What does this area represent? Okay, so let's practice drawing as well as finding areas. Draw a force versus time graph for a constant 5 newtons applied for 7 seconds, and state the impulse. 7 seconds here, 5 newtons here, and it goes like that. Impulse would be 35 Newton seconds. And also something you need to keep in mind is, you see how over here it said applied for 7 seconds, right? That doesn't mean it needs to start at 0 seconds and go to 7 seconds. It could start like over here at 10 seconds and it could go to 17 seconds. Either way, it gives you the same answer, okay? Impulse is force times change in time, not just time, change in time. So how much does your time final differ from your time initial? Okay, so a triangle pulse peaks at 30 newtons over 0.2 seconds. 30 newtons here, 0.2 seconds here. So this is 0.1. The middle, if you flip this like a rectangle, becomes 0.1. This thing times 30 newtons, or 3 kilogram meter per second, 3 newton seconds. Force ramps up from 0 to 10 newtons over 2 seconds. Okay, it stays that for 3 seconds, so till 5. Then it drops to 0 over 1 second, so then 6 seconds here. So first I find the area of this triangle. 1/2 times 2 seconds times 10 newtons, or 10 newton seconds. And then the area of this rectangle would be, so first I have to calculate the base, right, which is 5 seconds minus 2 seconds. 3 seconds times 10 newtons, because that's the height. So the base here versus the height. What am I even writing? 10 newtons, right? So 30 newton seconds. And then the triangle here, this last triangle, 1/2 times 1 second. Okay, from 6 seconds minus 5 seconds, 1 second. And then that times the height, which is 10 newtons. So this should give you about 5 newton seconds. So the total area, which is the total impulse, 10, 5, 30, 30 plus 10 plus 5, 45 newton seconds. Okay, so that's how you solve those graphs. Now, let's look at momentum and velocity versus time graphs, okay? So remember how we went over velocity versus time graphs before? And we determined that the area under those graphs was the what? You guys remember? The area under velocity time graphs was displacement, and the slope of those graphs was acceleration. So a P versus T graph, which is, instead of newtons here, it's a momentum, okay? So momentum as a function of time. How much does it change as a function of time? So what is the slope of this kind of graph going to be? Well, so we know the units here are going to be the y value, delta y over delta x. The y value is going to be in momentum, right? So kilogram meter per second over in seconds, so over seconds. So the slopes of momentum time graphs are the newtons, okay? They're the force. That's the slope for momentum time graph. And that's how you get momentum, right? I mean, that's how you get force. And for a velocity versus time graph with a constant mass, you just have to multiply that by m to get the momentum, right? Because it's m meter per second, right? So if you multiply that by kilograms, you'll get kilogram meter per second for a velocity time graph for a constant mass. You don't need to worry about that too much right now, but we won't even cover it that much in depth because it's not really tested, but just keep it in mind. Okay? So we need to pull the collision off the axis. Momentum is 12 kg meter per second until t equals 2 seconds, where it drops to 4 by t equals 2.5 seconds. And then it stays there. A collision, so it starts at t equals 2 seconds, right? That's why it changes. Otherwise, why would it change? The momentum change is what causes a collision. So we start here. Duration delta t, 0.5 seconds. So change in P, or change in momentum, right, is momentum final, which is 4, minus momentum initial, which is 12. So negative 8 kg meter per second. Okay? Then your force is equal to your delta P, so negative 8 over your time, where that changes, which is 0.5. So your force is about negative 16 newtons. And this negative just means it's opposing the motion, okay? Not for the motion. So if, for example, if you crashed into a wall, the wall would oppose your motion, right? You would have to stop. So the force would be directed against you. All right, so let's look at some graph examples here. A P versus T graph is flat at 20 kg/meter per second and then drops to 5 over 0.4 seconds. Okay, so it's flat at 20 kg/meter per second, then drops to 5 over 0.4 seconds. So 20, and then 0.4, it drops to 5. Okay, the collision force is just the slope of this graph, right? Which is going to be 20 minus 5 over 0.4 minus 0. Oh wait, I think I got that wrong. Yeah, so 0, 20, right? And then 0.4, 5. So I guess it'd be a bit easier if I did the other way. 4.5, or wait, 5 minus 20 over 0.4 minus 0. Negative 15 over 0.4, which would give us about, let's see here. So negative 15 divided by 4 over 10, right? We can approximate this to be negative 37.5 newtons. Okay, and how do we find this? Why did I use the slope? We know that the slope of a momentum time graph is force, right? I just showed you that. So that's how you get that. This means it's opposing motion because it's negative, right? On a V versus T graph, a 3 kg object goes from 6 meters per second, okay, to 2 meters per second over 0.2 seconds. Find delta P and the force. Delta P here is just going to be a change in P, right? So what's that going to be here? P final minus P initial. And we know that to be M times V final minus V initial, right? I showed you guys before. So mass here would be times 6 because that's, or 2 because that's our velocity final, right? Minus what? Our velocity initial is 6. So negative 4 M. Or, since we know M, times 3, negative 12 is our delta P. Okay, makes good sense, right? That's it. And then the force here would just be delta P over delta T, right? Just from the momentum impulse equation. So negative 12 divided by how much time did this happen over? 0.2 seconds. So the force here would just be about negative 60 newtons. Okay, so that's how this works. This is kg/meter per second. Now let's look at question 3. Momentum changes sharply between t equals 1 second and t equals 1.2 seconds. When does the collision happen and how long does it last? The collision happens at 1.0 second, right? It starts at 1.0 seconds because that's when the momentum seems to start changing. And then it lasts for 0.2 seconds because that's 1.2 seconds minus 1 second. Okay? And yeah, that's it. So next time, we'll be going over more in-depth momentum, okay? Including 2D momentum and motion using momentum as horizontal, vertical, as well as more complex facets of momentum. So stay tuned for that, and I'll see you in the next video. Make sure to subscribe so I can keep helping people like you and keep going with my videos.